Welcome everyone. Today we're going to start looking at section 12.6, which is our graphs for cylinders and quadric surfaces in 3 dimensions. Okay, so definitely getting some common types of surfaces graphs that we're going to see and hopefully try to visualize over the course of the semester to work with our different integrals, derivatives, and whatnot in 3 dimensions later. Okay, so again, this is going to start to get us working on graphing in 3 dimensions. Okay, so we're going to look at section 12.6. You call it cylinders and quadric surfaces. Okay, so basically this is just getting us started with more graphing in 3 dimensions. Okay, and so when we start to work on this, we'll come back to, sorry, this would be cylinders, if I can spell cylinders, there we go, and these quadric surfaces. We'll come back to that cylinders, right? But these quadric surfaces, these are going to be graphs in 3 dimensions, right? So that's where we get this surface. Instead of just like a line, a curve. Now that we have 3 dimensions, it's going to be more of a surface. I kind of think like a sheet of paper being folded, being manipulated in space. Okay, graphs in 3D given by an equation involving the squares of x, y, and or z. Okay, so again, some or all of these terms will be squared, right? Hence quadric or quadratic was when we had an x squared involved. So again, similar with x, y, or z being squared, we can start to see those equations. Okay, and so typical forms, and there's other varieties, but we're going to see something like ax squared plus by squared plus cz squared is equal to 1. Okay, or again, we might have a linear term somewhere, ax squared plus by squared plus, I'll call it dz is equal to 1. Which term is linear or squared, right, can change. It just depends on how we start to orient our graph, but these are kind of formats that we'll see. And likewise, we might have cases where our equation is equal to 0 instead of 1, instead of some constant, right? And we can have that same work where one or even more than one of those terms may be linear, okay? But again, this combination of quadratic terms, x squared, y squared, even z squared, and linear terms possibly, most cases will have equal to 1 or 0, are typical forms there of quadric surfaces. Okay, quadric equations in 3 dimensions and 3 variables, which when we graph will give us surfaces. Okay, I'll put dot, 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 because again, we can start to take different formats, different organizations, and see similar types of graphs. Okay, and so now when we go to graph, an equation of any form really in 3 dimensions, right, or basically in 3 variables, and we start to see that x, y, and z are involved. Typically, when we go to graph, we can use traces or later, we'll start to call these level curves, to form a kind of structure, a framework for our surface that we're working to graph, that we're working to create, okay? And then so in that process, what we're going to do with these traces, with these level curves, we're going to let one variable be a constant, right? For instance, let z equal 0, z equal 1, z equal 2. And you can do the same thing with x, y, right? And just kind of slowly but surely put those different pieces together, right? Then graph, consider, right? Visualize the graph in 2D from that equation. And again, I know that's kind of abstract in this statement. So let's go through an example and we'll start to put this together and see some of these common shapes and figures that we'll have to manage, okay? All right, so now we put that off to the side. So for example, let's borrow one of these equations from the book. Let's consider this function. Let's look here, number 12, page 880. The equation 4x squared plus 9y squared plus 9z squared is equal to 36. Right, and so like I mentioned in that beginning portion of the lecture, we have a quadratic equation, a quadric, I guess you'd say, equation, x squared, y squared, z squared, all terms being squared, right, all positive in this particular instance, equal to some constant 36, right? So in our problems, it's either going to be equal to a number or right, 1 later, or 0, okay? So if I want to kind of get this into our more common format, I can divide every term by that 36. And now we have x squared over 9 plus y squared over 4 plus z squared over 4 is equal to 1. So a more common format. X, y, z on one side, all quadratic, x squared, y squared, z squared, all positive in this instance, equal to that 1. All right, so a more standardized form. Okay. So with that equation, let's think about some of our traces. Right, some of these level curves. And let's let z be different constants. Okay, so for instance, here, let me grab my pen. When z is equal to 0, right, our equation looks like x squared over 9 plus y squared over 4 plus this z squared over 4, which was chosen to be 0. I made that choice. So this corresponding to what the curve would look like in that x, y plane alone. Okay. And so with that equation, x squared over 9 plus y squared over 4 is equal to 1, with that z being 0. And this is where it's going to tie back into some work you may have seen before in pre-calculus, intermediate algebra, geometry, somewhere along the line, hopefully. are conic sections, right? So the graphs for a circle, an ellipse, hyperbola, right? Those formats for those equations, we're going to start to see here, even played out in our 3 variable format. You may start to recognize those, okay? And so in this case, this is going to be an ellipse, okay? And in the x, y plane alone, with center at the origin, we're going to go out in the x direction by 3 units. 1, 2, 3, both positive and negative. In the y direction, we're going 2 units, right? The square root of that value. And again, I know that might be a jump in recognition, but if you go back to conic sections, we can start to fill in some of that information, right? So we're going to get this ellipse. That egg-like shape, right? Like so. And so then in 3 dimensions, though, now you have to bear with me. Thinking about in 3 dimensions, when z equals 0, so we're in that xy plane, we're going to get that ellipse lying flat on that ground map, okay? And then we're going to do it again. We're going to say, okay, let's let z equal, and let's do something a little big. We can do 1, but let me jump a little bit. Let's go z equals 2, okay? So then x squared over 9 plus y squared over 4 plus 2 squared over 4 equals 1. Okay, that means x squared over 9 plus y squared over 4 plus 2 squared is 4 over 4, that's 1 equals 1. Something interesting here. X squared over 9 plus y squared over 4 is equal to 0. So without that 1 over there, now it's starting to look a little bit peculiar, a little strange. Okay. And this is only going to be true at a point 0, 0. That's the only value that satisfies that relationship. And that's going to take some time to think about. Okay. Because you can take the square root on both sides. And the negative is going to be an issue, right? Because I can't take a square root of a negative. So you have a y squared, always positive, equals a negative of something x being squared. Well, the only way 2 squares can be equal if we're doing a positive negative is 0, because 0 doesn't have a sign. Negative 0, same as just 0. So that's the only value that's going to work. So this kind of leads us to this point. Oh, cross that out, sorry. That z was 2, pardon me, x and y 0. So if you don't mind me sneaking back up here, when we get to that point, x and y is 0, the y value 2. And so here, had we done that z equals positive 1 or even any fraction decimal in between, z can equal a half, 3/2, 3/4, whatever you like, we can go through this process And what that would do, okay, is all it's going to do is going to shrink the size of that ellipse. Okay, so even though we didn't trace it, if we would have done z equals 1, it would have been some ellipse like so. And so right for z equals 1, we would have gotten a smaller ellipse like so. And again, it's a long process, I know. But what we can do that work. And then now instead of z's, maybe we let x be a constant. And again, you're gonna get another kind of family of ellipses, okay? And you can do it both with z is positive, z is negative. Start to cycle through, you're gonna get ellipses smaller, going down below the xy plane, okay? And like I mentioned, we get this kind of framework for what this graph's gonna do. And so as we start to put these together, thinking about those kind of connections that should have been extended out there, there we go, okay? But what we're gonna start to see, and again, this is where my graphing on paper is not that great. So I'll show you just a moment. A graphing utility you can find online. But what we start to find is that we get this ellipsoid, right? This 3D ellipse, right? Basically, it looks like an egg or a football, okay? But what we're going to have is this kind of family of ellipses. And again, it looks more like a cone here, right? But as we start to go below, okay? And then as we start to slice in other directions, and I know this graph's pretty horrible, so I'm gonna switch to the computer graphing in just a second. But we start to get this kind of three-dimensional figure, okay? And again, I know my graphing is not great, so bear with me, pretend that didn't go. So let's start to share another screen here, okay? All right, stop sharing that. Let's go here. All right, and so as we go through, let me start to share this. Okay, let me make sure it's set up. All right, and I'll put this website in our Canvas page as well. But here we have this GeoGebra.org, 3D graphing, okay? And then you may work with this in other courses. Keep track of what our axes are, where your X, Y, and Z are being represented. But if I put that equation, even I put that original 4x squared plus 9y squared, and again, plus 9y squared plus 9z squared equals 36. Or we can do the simplified form, the standardized form, 1/9 x squared, 1/4 y squared, or y squared over 4 plus z squared over 4 equals 1. It'd be that same graph, okay? And so now as we go, in this case, the x-axis is the red axis, this axis coming out toward us. The y-axis, sorry, I don't want to spin it. The y-axis, the green, 2 units there. And the z-axis, the blue, 2 units. So as we start to look, right, if I look straight down, that z-axis, there's, I don't know, it's kind of switched on us, so let's go this way, there we go. Right, so there's my positive x-axis, positive y-axis, 3 units. So this is what z equals 0, the overall outer body. But then as we start to do those different levels, when z equals 1, for instance, right, we're going to get a smaller ellipse. And then when z equals 2, right, it's just that point at the top. And if we look head on along that y-axis, again, in that xz plane, you can see my mouse pointer, another ellipse. And as we start to go through with different values for y, whether it be positive or negative, those smaller ellipses coming out. Okay? And we can even graph some of those to see those components. Okay? But we start to get these bodies. And so depending on the nature of our equation, we're going to see different types of shapes, and they're going to be most likely those conic sections, ellipse, circles, cones, okay, hyperbolas that are graphed out. So I'll put this link in our Canvas page, but also I want to show in the textbook where they have a lot of this information kind of condensed down, simplified for the different figures, okay? And so on page 877 of my text, turn off the light, see if that doesn't make it any better without the glare, right? So on page 877, these different graphs and the type. So what we had just done, an equation in this form, right? All terms being squared, right? All those traces are going to be ellipses. You can see those different traces, that framework, that wire frame of our graph. So when you have all quadratic terms equal to 1, all positive, it's going to be that ellipsoid, right? Other shapes, when we start to see, okay, one term's linear, z to the first in this case. Other two terms are quadratic. We have equal to that z. So in this case, this would have been, if I had brought this term over, we have a 0 on one side, all our terms on the other. And we start to get this paraboloid. Here, when one of those terms is negative, all quadratic, a hyperboloid of one sheet. Right, that's all together one sheet of paper I can use to form it. If I sneak down, if we have two negative quadratic terms, one positive equal to 1. Now a hyperboloid of 2 sheets, right? 2 sheets of paper that I would need to use to create that surface, that figure. And then another interesting one here, the kind of saddle looking shape, right? Like that pink Pringles chip. Upwards in one direction, downwards and curvature on the other. 2 quadratic terms, opposite signs, 1 linear term. If we brought this term over, we have equal to 0. So a lot of these different items to consider. And so for today, just kind of letting you take a moment, take this page in to consider. As you can see, my graphing is not great by hand, so I'm not going to hold you accountable either for how perfect, how great your graphs look. What's more important is that you can kind of start to see some of these formats and slowly but surely pick up on what figure, what shape we're dealing with, right? It's not going to be absolutely important right now. We memorize exactly right away, but slowly but surely, because we're going to take some of these equations into the next couple of sections, right? And we want to be able to kind of imagine that surface and how it relates to different calculations and actions that we'll be going through, okay? All right, so I'll leave it at that. I'll put those notes, that discussion up on Canvas, this lecture as well, and definitely take some time to look over this page to get familiar with these equations, okay? All right, crew, if you have any questions, concerns, let me know. Email me, come to my office hours, meeting time with students, whatever you want to call it. But definitely get your questions answered if anything should come up. All right, take care. Talk to you more soon.